Hey there! So, in this lesson, we'll be talking about the line of best fit. Now, what is the line of best fit? Well, in short, if you have data points on a graph, the line of best fit is just a line that goes through all the points, the best fit that goes through as closest to all the points as possible. So, here's a line of best fit here, here's a line of best fit here, and over here. Well, let's look at the actual definition. It says here, the measure of dependence between two random variables. Linearity can vary by some degree. However, a pattern is usually observed on a scatter plot graph. So, if you can see a pattern in the scatter plot graph, you can put a line of best fit. So I see a pattern here, I see a pattern here, I see a pattern here. The closer the pattern is together, the stronger the correlation is. So this is very strong correlation, and this is a weak one because you can see a pattern, but the points are kind of split off. This one's a strong negative, and it's negative because it's going downwards. Here's a weak negative. It's going downwards, and the points are a bit off away from the line. That's why it's weak. Here's moderate. They're pretty close together. And here you can't even make out a pattern. So there's no correlation. Okay, let's talk about the correlation coefficient, or otherwise R. Well, to calculate this, it is a series of complex calculations, and I want to emphasize the complex calculations. They don't even give me the formula in the book. I can only guess what the formula is, but all you need to know is if you put this through your computer or an online program or graphing program, sometimes they give you the value of R, and that is the correlation coefficient. It's often a feature added to most graphs, such as spreadsheets and calculators, which is true. The R represents how far the points are on average from the best fit line. So basically it asks you how scattered those points are relative to the best fit line. And here's just a chart that gives you an idea as to whether the correlation coefficient is either strong or weak or none at all. The R relates to the slope of the line, not the best fit. It does not indicate whether it is a direct relationship between variables. That's true. Here are a couple of examples. Here is an R of 1. And the reason why it's 1 is because it's very tight. As you can see here, the points, they're very close to the line. And it's positive. Here is negative 0.94. And the points are very close to the best fit line as well. Very close. Not as strong as this one. The closer it is to 1 or negative 1, uh, that tells you how strong or how straight the line is. Here it's 0.45, it's positive, so it's going upwards. And it's 4.5, so it's like moderate, but you can still see a pattern, but it's still kind of scattered. Same thing down here. This is sort of weak because it's zero. If you look at the correlation, it's 0.18, and if you look at the chart again, it tells you whether or not it's weak or strong. And here's a negative. Here's no correlation because you cannot make out a pattern. And here also, if the line of best fit is basically flat, that means it has no correlation. Now here's some examples. This table, oh, just so you know, the line of best fit, in most cases, in most problems, we're just gonna use maybe 2 points just to make an estimate as to what the line of best fit is. You'll see in the next couple examples. So the best way to learn the line of best fit is to do examples. So example 2, line of best fit. This table is posted in a fitness club and shows and estimates the maximum possible heart rate during intense physical activity based on a person's age. So we have the maximum heart rate here and the age. Now, if you're wondering which is the dependent variable, it's the age, because the age does not change regardless of what you do, but the heart rate does. If the age is different, then the heart rate would change. That's why on this graph, age is on the x-axis and the maximum heart rate is on the y-axis. As you can see here, it's almost nearly a perfect line. So essentially, if I want to get the line of best fit, I can just choose 2 points and get the slope from that. It says to make it and classify the correlations. Okay, this one here already classified it. The person's age increases by 10 years and estimates the maximum heart rate decreases by 10 beats per minute. The points line up perfectly in a straight line, so there is a perfect linear correlation with a negative slope. So it's a negative slope and it's almost linear. So it says here to use an algebraic method to determine the equation of the best fit line. Let x be your person's age in years, and y the estimates of the maximum heart rate in beats per minute. So you'll need the general equation of line. If you don't already know this, this is the general equation of line. You learned this in grade 9. And we'll be using this equation to figure out what our line of best fit is. Or in general, it's just basically we're gonna find the point. We're gonna find the just the slope of any 2 points. So what I'm gonna do here, let me get my pen tool. Go to pencil here. What I'm going to do here, I'm going to choose 2 points on the line. So what I'm going to do, I'm going to choose the first 2 points here because it's a straight line. So pretty much if I get use these 2 first points, the line's going to pretty much go through all of them in a sense. So I'm just going to choose 2 points. So the first point I am going to choose is, okay, let's choose a point here. Let's choose point 1, and that will be 20 and 200. Point 2, we'll choose 10 and 210. Okay, good. So we got 2 points, and we grab those 2 points from here, from here's the points I grabbed. Those are the ones I'm using. I can use any 2 points, just so you know, but I chose those first 2 points because most examples choose the first 2 points, and why not? Ideally, I guess the first point and last point are probably better to choose, but I'm just going to stick with the first 2 points for now. So let's calculate the slope. So slope, we often designate it as m. I like to keep consistent with the variables. And if you guys remember the slope formula is rise over run, or basically y2 minus y1. That's in terms of points, and x2 minus x1. So you can consider this, well, this would be x2 and y2, and you can consider this x1 and y1 here. So if you drop that into this formula, we have 200 minus 210, and this will be 20 minus 10, which gives me -1. So a slope of -1. Okay, that's good. So from this point, okay, so first part, okay, generate, okay, the line of best fits. Okay, so now we have the slope. We have what m is. M equals this. Now I'm going to make it over here. M equals -1. So we have m, good, right? And all we need to find is b. So we need any point. We can use any point on the line. I can use any point up here, or I just choose, why not just choose this point right here? Any point, you can use any point. So I'm just going to choose that point. And what I'm going to do is first I'm going to write down the equation of the line, and I'm going to rearrange it. So it'll be b. So over here, I'm going to bring the mx to the other side of the equation and leave that y there. So I have b equals y minus mx. And I'm going to choose, I'm choosing this point here. And here y is equal to 210. So bracket 210 minus, and we have our m is -1, and our x, in this case, will be 10. And that will equal 220. 220. Okay, so now we have y, and now we have b. And that's all you need for the equation of the line. So we just drop that into the general equation of the line, y, and put our m in, which is -1. there, x, and our b is plus 220. And there we go. That is the equation of the line. Okay, let's read the next part. Describe how to use the equation. To estimate the age predicted maximum heart rate, subtract a person's age from years from 2020. Okay. So basically, in short, we're going to use the equation to make a prediction. It says here, suppose a person's age is 10 years old. So if we know the person's age is 10 years old, we can drop it into the equation and find out what the heart rate is. Remember, y is the heart rate and x is the age in the equation. And we have the equation right up here. So we can figure out what the heart rate is by just dropping x in. So it's -1. That's where your x is supposed to be. Actually, maybe I should put the equation over here so you can see what it is. -1x plus 220. That's the equation that we are using. And we're dropping the numbers in here. This will be 10 years old plus 220. And that should give us a value of, oh, hold on, 210 here. So at 10 years old, you have a heart rate of 210 beats. Let me see if it's per minute. It's beats per minute. Yes, beats per minute. Okay, great. Let's move on to the next problem. Oh, more lesson. Here we go. Linear regression. Okay, let's read the problem. Well, first we talk about linear regression. Linear regression is a software, as I mentioned earlier, is a software that that's various complex calculations to determine the equation of the line or the best fit. So basically, if you on Excel or any program, if you click on linear regression, it will automatically give you a bunch of information. It will give you the correlation coefficient. It will give you the slope, and it will also give you the y-intercept. That's what linear regression does. It's a very useful tool, and all it is just a tool on your calculator or on a graphing program. So the easiest way to learn is to do problems. So last year, 12 randomly selected students took a mathematical aptitude test before they began their college mathematics course. Their result on the aptitude test and their final mark in the course are shown in the table. All scores are out of 100. So here are all the scores here. And what I did is I went on Desmos. Well, actually, this is actually a picture of this table. And it actually, if you pop this into Desmos, I think I did pop. Well, if you pop this to Desmos, you will give you this R, which is R.77. It will give you the slope, and it give you the vertical intercept. And you put that together, you have the equation of the line. So linear regression is a very, very useful tool. It gives you a lot of information. So it asks you, how well does this linear equation fit the data? Well, it gives you what R2 is. R2 is 0.77. And if I get the root of that, I get 0.87. 0.87 is, well, this number here is in between 0.67 and 1. And if you look up at a chart, between those two values is considered strong positive correlation. Now, here's the fun part. If Hannah scored 75 on the aptitude test, what would you expect her mark to be in her college mathematics score? Well, you know what? We have an equation for that. Our equation is y equals 0.974x plus 0.014, where y is the score. If you look up here, it's the mathematical, well, it's the math mark, as they say, math mark. and X is the aptitude test. And I'm getting that from here, from this graph here. This is the Y, and this is the X. Here is a math mark, and here's aptitude test. And on this question, it tells you what the aptitude test is. It says it's 75. So all you have to do is drop that number into our equation, and it's 0.09, oops, not 0, 0.974, and our score was 75, or her score was 75, plus 0.014, and that should give us a value of 73. 73.064. That is her mark there. Okay, next question. Oh, this is sort of the same question in a sense. It says here, if Petro scores a mark out of scores 40 on the aptitude test, what do we expect his mark to be in college and a mathematical course? So this is the exact same problem as the previous one. The only difference is this is called extrapolation. Extrapolate. If you look at the scores here, the highest score is 95, and the lowest score here is 50. So 95 to 50. Anything outside that is considered extrapolation. And you just got to be careful when you make these estimates with extrapolation, because they can vary wildly. But otherwise than that, it's basically done the same way. So I'm gonna do here y equals 0.974 x plus 0.014. I drop a number in, which is 0.974, bracket. Here is 40 plus 0.014, which gives me a value of, let me take a look, 38.974. So 38.974. And this is extra, extra, extrapolated, because it's outside our data points. Okay, I think that's about it for this lesson. Yeah,